In this video, we are going to deconstruct self-attention, one of the key ideas behind modern language models. Instead of treating each word alone, self-attention lets a model ask for every word, which other words in the sentence matter the most right now. Our goal is to walk through a tiny example step by step so you can actually see the numbers move and watch a simple sentence turn into a rich contextual representation. I will keep the math gentle and focus on the intuition behind each step. Let's start with a very human problem, the problem of context. Take the word bank. In the sentence, the bank is on the river, bank means the side of a river. In the sentence, I need to go to the bank, it suddenly means a place for money. The spelling is the same, but the meaning changes completely depending on the neighbors around it. A computer does not understand this automatically. Self-attention is the mechanism that helps the model look around a word and decide which meaning fits best in that situation. Here is the big picture of what self-attention will do to our sentence. We start with input embeddings, which are just number vectors for each word. Then we project those vectors into three roles called query, key, and value. Next, we compare every query with every key to get similarity scores. We scale those scores down so they stay in a comfortable numeric range. Then we apply a function called softmax, which turns each row of scores into a set of percentages that add up to 100. Finally, we use those percentages to blend the value vectors. The result is a new contextualized vector for each word, where the meaning of the word has been influenced by the rest of the sentence. For the rest of the walkthrough, we will use a tiny sentence. I love cats. The model does not see words, it only sees numbers. So first, each word is looked up in a big dictionary of vectors and turned into a row of numbers. In our toy example, each word is represented by only 4 numbers. So our embedding table has 3 rows, 1 for each word, and 4 columns, 1 for each feature. That means X is just 3 by 4. In a real language model, these numbers are much larger. The model dimension, often called D model, is not 4. It is usually something like 512, 768, or even more. That means each word is a vector with hundreds of numbers, not just 4. The height of this matrix can also be big. Instead of 3 words, a real model might process a sequence of 256 or 512 tokens at once, so X could easily be 512 by 768. Our 3 by 4 example is just a tiny friendly version, so we can see every step without drowning in numbers. Inside one attention head, we also choose a smaller size called the head dimension, usually written as dk. In our example, we set dk equal to 2, just to keep the math simple. In real models, dk is often 64 or 128. So remember the shapes in this demo are tiny on purpose, so you can focus on the logic, not on huge matrices. In the full transformer, we also add a positional signal to each word, so the model knows who comes first, second, third, and so on. In this demo, we are ignoring that part on purpose, so we can focus only on the attention math itself. Now we introduce 3 important players, the weight matrices. There's one for queries, one for keys, and one for values. You can think of each one as a small filter full of learned numbers. In our toy world, each word starts as a 4-number vector, and we want each head to work in a 2-number space. That means each weight matrix, W sub q, W sub k, and W sub v, is 4 by 2. When we multiply x, which is 3 by 4, by one of these 4 by 2 matrices, we get a 3 by 2 result. So q, k, and v each end up with 3 rows and 2 columns. In a real transformer, these shapes are much bigger. Imagine a model with D model equal to 768 and dk equal to 64. Then each weight matrix W sub q, W sub k, and W sub v would be 768 by 64. There is one trio of these big matrices for every attention head, and there can be 8, 12, or even more heads in a single layer. During training, these weight matrices start with random numbers, and gradient descent slowly adjusts them so that the model gets better at predicting text. We are freezing them here just to watch what one trained head does. The query weights learn how to turn a word into a search request for information. The key weights learn how to turn a word into a kind of label that can be searched. the value weights learn how to represent the actual content the word is carrying. Our little 4x2 matrices are just cartoon versions of those huge, real ones. They let us see the exact same operations the big models do, but with numbers that fit on a slide and in your head. We now multiply the embedding matrix X by each of those three weight matrices. When we multiply X by the query weights, we get the query matrix, often called Q. Each row in Q belongs to one word and tells us what that word is looking for. Multiplying X by the key weights gives us the key matrix, K. Each row in K tells us how that word presents itself to others, almost like a name tag. Multiplying X by the value weights gives us the value matrix, V, which holds the information that will actually be mixed and passed forward. So now every word in I love cats has three two-number vectors, a query, a key, and a value. This is the starting point for the actual attention calculation. Next, we want to know how much each word should pay attention to every other word. To do that, we compare every query with every key using the dot product. You can think of the dot product as a simple similarity measure. For two number vectors, the dot product means we multiply the first coordinates together, multiply the second coordinates together, and then add the results. If two vectors point in a similar direction, their dot product is large. If they disagree, it is smaller. So we take the query for I and compare it with the keys for I love and cats. That gives us the first row of scores. We do the same for the query of love and for the query of cats. The result is a small 3x3 table of raw similarity scores. Row 1 shows who I cares about, row 2 shows who love cares about, and row 3 shows who cats cares about. For longer sentences, these dot product scores can become quite large. Large numbers going into the softmax step can make the model unstable and too certain about a single choice. To avoid that, we scale the scores down. We divide every score by the square root of the head dimension. Our head dimension is 2, so we divide each score by about 1.41. After this division, the numbers are still in the same pattern, but they are smaller and more manageable. This simple scaling trick keeps training stable and makes the attention mechanism behave nicely, especially when the model has many heads and many layers. Now we want to turn each row of scaled scores into something we can read as percentages. That is what the softmax function does. For one row, here is the recipe in words. First, we take each score and feed it into the exponential function. That means we use the famous constant e, about 2.718, raised to the power of that score. This makes all the values positive, and it amplifies differences, so bigger scores stand out even more. Second, we add up all these exponential values for the row. Third, we divide each exponential by that total sum. The result is a set of weights that are all positive and add up to 1. You can think of it like turning raw points into vote percentages for where the attention should go. Let's walk through the softmax for the first row, which belongs to the word I. The three scaled scores in this row are roughly 1.41, 2.83, and 2.83. First step, exponentials. The exponential of 1.41 is about 4.10. The exponential of 2.83 is about 16.97. We have that same value twice for the other two positions. Second step, we add them 4.10 plus 16.97 plus another 16.97 gives a total of about 38.04. Third step, we divide each exponential by that total. 4.10 divided by 38.04 gives about 0.108. Each 16.97 divided by 38.04 gives about 0.446. So I gives around 11% of its attention to itself and about 44.5% each to love and to cats. We repeat the same process for the second row, which belongs to the word love. Its scaled scores are roughly 2.83, 5.66, and 5.66. After the exponential step, the first value becomes about 16.97, while the other two jump to around 287 each. When we sum them, we get a total a bit above 591. Dividing each exponential by that total gives us weights of about 2.9% for I and about 48.6% for love and for cats. The third row, which belongs to cats, has the same pattern of scores as row 2, so its weights are identical. When we stack all three rows of weights together, we get the full attention weight matrix. Each row shows how one word distributes its attention across all the words in the sentence. You can think of each row as a spotlight. It decides how strongly this word shines its light on every other word when updating its meaning. We are now ready for the final step. Remember, the value vectors hold the actual content we want to move forward through the network. The attention weights tell us how strongly each word should borrow the value of each other word. On this slide, you see our attention weight matrix on the left and the value matrix on the right. To get the final output, we simply multiply the weights by the values. In other words, output equals weights times V. For each row, this multiplication is just a weighted average of the three value vectors, using that row's attention weights. The first row mixes the values of I love and cats using the weights from the first row. The second and third rows do the same thing using their own weights. Conceptually, this is where the magic happens. Each word builds a new vector by blending the content of all the words it decided to focus on. In the next slide, we will zoom in and see the exact numbers for these new vectors. Let's look closely at the new vector for the word I. We will compute its two coordinates using the first row of attention weights and the three value vectors. For coordinate 1, we take 0.108 times the first value for I, plus 0.446 times the first value for love, plus 0.446 times the first value for cats. That gives 0.216 plus 0 plus 0.892, which adds up to about 1.11. For coordinate 2, we take 0.108 times the second value for I, plus 0.446 times the second value for love, plus 0.446 times the second value for cats. That gives 0 plus 1.784 plus 0.892, which adds up to about 2.68. We do the same thing for the second and third rows. Because their attention weights are the same, the resulting vectors for love and cats are identical. Roughly 1.03 for the first coordinate and 2.92 for the second coordinate. At the bottom of the slide, you can see the final output matrix. Each row is a new contextualized vector for one word in the sentence. All the steps we did can be summarized in one compact formula that you may see in papers. It says attention of Q, K, and V is softmax of Q times K transpose divided by the square root of dk, all multiplied by V. The messy arithmetic on this slide is just one concrete example of that single formula in action. Now let's compare what happened to the word I. At the beginning, its embedding was just a static dictionary entry, a four-number vector that meant I, the pronoun, but knew nothing about the sentence around it. That same vector could have appeared in I hate dogs or I drink coffee, and it would look identical. After self-attention, the new vector for I is a blend. Roughly 11% of it still comes from the original I value. A year well. About 44.5% comes from love, and another 44.5% comes from cats. In other words, the model no longer sees a naked I. It now sees an I who is experiencing love towards cats. To wrap up, let's zoom back out. Self-attention transforms generic word vectors into context-rich representations. In a real transformer, this same recipe is used with much bigger matrices, many attention heads in parallel, and many layers stacked on top of each other. It's the exact same logic you just saw, just repeated and scaled up. It does this by projecting words into three roles: query, key, and value, then computing how strongly each word should look at the others. The attention weights act like influence scores, telling us who matters to whom in this specific sentence. Finally, those weights are used to mix the value vectors and create new contextualized outputs. The end result is a sophisticated blend of a word's original meaning and the meaning of its neighbors. This is one of the core building blocks that allows large language models to understand nuance, ambiguity, and subtle shades of meaning in human language.